If you're a student, here's how you can save some of your time. The easiest way to score top essay marks like this is to just ask.
Welcome to this course on mastering technical interviews for software engineering roles. These interviews often hinge on your ability to confidently solve problems using data structures and algorithms, which can feel challenging without the right foundation. In this comprehensive course, Parth from Destination Fang will strip away the intimidation and equip you with the essential knowledge, starting with the core concepts of data structure, algorithm, and fundamental analysis like time and space complexity. You'll learn how to judge an algorithm's efficiency using Big O notation and apply this important skill to code blocks. The course covers almost every major data structure and algorithm pattern, from arrays, linked lists, stacks, and queues to advanced topics like trees, graphs, dynamic programming, and backtracking. So, good luck learning.
Hello friends, hope you are having a fantastic day today. This is going to be a 50-hour long course that contains everything there is to know about technical interviews, data structures and algorithms. There are about 20 concepts that I have created that comprise the entirety of technical interviews, and that contains different data structures, different algorithms and different coding patterns. We are going to cover each and every one in very much detail. We will understand the concept for them, and then we would solve lots and lots of interview problems associated with that. By the end of this course, you would have solved close to 200 most asked, most liked and most popular interview problems, and you would be able to solve majority of technical interview problems out there, and then it's just a matter of sheer practice that you will have to do on your part. I can guarantee you that this is going to be a very high quality in-depth course where it is completely beginner friendly, and we will go deeper and deeper into the most advanced topics, and I will try to explain it in as much detail as I can, so you can be absolutely prepared for anything to come in your technical interviews. Now a quick introduction about myself. My name is Parth Vyas and I have bachelor's and master's in computer science. I have been in the IT industry for close to 10 years now, and I have worked at companies like Microsoft, RBC, Nokia, and currently working as a solutions architect for Cineplex. I have joined my career as a junior developer and have gone through multiple transitions. I have been absolutely blessed by a lot of important mentors who have guided me correctly in my career, and this is something me giving back to the community. Now, I also run my own YouTube channel named Destination Fang, and I would highly encourage you if you can go and support me on that channel as well. I teach about how you can go ahead in your career and how you can ace your technical interviews, behavioral interviews and system design interviews, and your support matters a lot for me, so it can motivate me to keep making more videos like this. On top of it, you can stay up to date on the latest and greatest things that I'm currently working on. Few fun facts about me: I love going on hikes, I love watching movies, and I love playing with my twin daughters. I am based in Canada, and this is a beautiful country, so if you get a chance to visit, please come and see it anytime. Now, I would not deviate from the main topic, that why we are here. So without any delay, let's get started. Now, what is DSA? DSA stands for data structure and algorithm. Now, everything in computers is made out of data. These are the bits and pieces of zeros and ones that hold all the information. It can be a text or a book or a PDF or the video you are watching. Anything can be represented as data, and the way we store and organize the data is referred to as data structures. Now, there are many different ways of storing data. You can store them in a straight fixed given format that can be defined as array. You can have one bit of data live over here, next live over here, and after one the next lives over here, but this guy does not know where this guy exists, and that's an example of linked list. And there are bunch of other different ways to understanding different data structures. Now, there are linear data structures, non-linear data structure, hierarchical data structures, hash-based data structures, and they all have different purposes, which we will learn more in the classification of data structures. Now, let's understand that what is algorithm. Algorithm is nothing but following step by step to complete certain procedure and achieve an expected outcome. Now, this can be anything. If we strictly talk about from the perspective of computer science, there are algorithms that do certain things really well, like sorting items, searching any particular item in the existing given data structure, recursion, dynamic programming, greedy approach, divide and conquer, and these are all the strategies that we typically use in our day-to-day operations as well. We just don't realize that these are algorithms. And then there is the combination of data structure algorithms that help us solve many complicated problems. So that's why the companies that are substantially large in the IT industry, these are the FANG companies or top tier IT companies, they usually build products that scale up to millions and billions of users. And they want to have the most efficient, most optimal approach to any given problem. And that's why they love asking these questions to understand the technical prowess and proficiency of any candidate. And that's where you need to be learning about these things. Now, how does a solution can be defined as optimal? Well, there are two things that defines that, and that is called space complexity and time complexity, and they are usually referred by big O notation. Now, we will understand the full theory on that in one of the sections, but how does companies typically evaluate your solution? They are looking for number one, whether you can reach to the optimal solution or not. That's a basic criteria, but that is not just the only criteria. Now, in a typical interview process, you are expected to go through somewhere between 3 to 5 rounds of technical interviews, each lasting about 45 minutes to 1 hour. And for each of the interview, you are expected to solve anywhere between 2 to 3 medium to hard DSA problems. Now, you are being judged based on your thinking abilities, your communication, whether you are a good person to work with. Can you think of different scenarios, different edge cases? Are you able to come up with the optimal solution? What does your approach looks like? If you have a suboptimal solution, can you reach to that optimal solution? Can you ask for proper hints? Can you convince your recruiter or interviewer about your solution? Can you walk through it? Can you code it out? And you know, the complicated part is they typically don't give you a full IDE or editor. They typically ask you to solve this problem on a whiteboard if it's in person, or on a Google Doc if that's going to be a virtual interview. So that's why there are a combination of skills that you will have to accumulate throughout this course and your preparation journey to be able to clear multiple different technical interviews. And we will learn that in the next section. Now,
هەموو بەیانیەک تۆ هەڵبژارنێک دەکەی خراپ نییە.
Good enough.
بۆچی بەکەم ڕازی دەبی جیلێت فیوژن 5 پرۆ هەڵبژێرە لەگەڵ پێشدەمی ئاسان بۆ چەمانەوە.
how do we even judge an algorithm? Well, there are three things that we are looking for. First one is the accuracy of algorithm. That is quite straightforward, that if I expect my algorithm to generate pizza or find the shortest number out of all of these given numbers, if it is exactly doing that, which means my algorithm is accurate, and it needs to do that for all the different edge cases and all the different scenarios. Second thing is time complexity, and third thing is space complexity. So first, let's understand that what is time complexity through an example by these deck of cards. Time complexity is nothing but how much longer will it take for you to complete your algorithm or your task if the number of inputs keeps on growing larger and larger and larger. Let's try to understand that currently I have these deck of cards and they are currently just randomized. If I lay them flat on a table, and let's say that for simplicity I'm trying to figure out that where does heart of 6 lies amongst these cards. Now I don't know, but I can keep on opening all the different cards randomly until eventually I found out to a card that is heart of 6. And notice that I found heart of 6 right here. But how many cards did it took me to find this value? It's just like finding a needle in a haystack. You need to go one by one. And if I had like million cards and all different unique entries, it might take me like million attempts before I reach to the card that I'm particularly looking forward. So in this case, we can notice that the time it takes for me to complete the expected task increases linearly with the increase in the number of inputs. So we can call this time complexity of big O of n. Now big O is the definition or a way we write the time complexity and space complexity, and we are going to talk all about that in a separate topic. But now let's just say focus towards this. Now let's see that how does time complexity change based off of how we have our data being scattered or how we change our algorithm. Let's take an example. Now in this case, we are going to sort all of these cards in ascending order, and then we are going to lay them flat once again on our card. So this is going to be the smallest value, and then we are going to keep on adding all of these values on this table. Now notice that in this scenario, once again we are trying to find that where does heart of 7 is present in this deck of cards. Now I don't know, I can't see them, but I know for a fact that this one is the smallest value, this one is the largest value. And if heart of 7 is present, let me just open the middle value. So middle value is heart of 6. So I know for a fact that all of these cards are definitely going to be smaller than 6 because it's already sorted. So I don't even need to look at these cards. I can ignore all these 4 cards and then I only worry about these 3 cards. Once again, I'm going to open the middle card and this one is heart of 8. Now I know because this is sorted, so these two values are always going to be greater than heart of 7. So this card has to be heart of 7, the lucky card. And that is what we currently have on our table. Now notice that once again we had again 8 or 9 cards, but we only needed to open 3 cards in order to find the card that we were looking for. This one is an example of logarithmic n time complexity. Why it's logarithmic n? Because with every single task or every single step we make, we are essentially eliminating 50% of all the inputs in one go. So here we eliminated 4 cards, then from the remaining 3 we eliminated 2 more cards. If we had million cards, in just one opening of a card, we would have eliminated 500,000 cards. In the second opening, we would have eliminated remaining 250,000 cards. So even if we have like 10 million cards, we can very quickly find the value that we are looking for, and that is an example of big O of log n time complexity. Now let's talk about some other time complexities and other examples. Now the most basic time complexity is a constant time complexity. Constant time complexity means that if it takes us, let's say, 1 second to do one job for 10 inputs, it will once again take us like 1 second even if we had 100,000 inputs. What's an example of that? Let's presume that we currently have this ice tray where we have bunch of different black chickpea beans associated with that, and they are currently placed in a sorted array, in a sorted bucket, and for each number it corresponds to total number of chickpeas being present. So like this one is first one, so it only has 1 chickpea. This one is second one, it has 2 chickpeas. Now in this case, if I have to figure out that show me 5 chickpeas, let's say that is what I want from my algorithm, I can very quickly say that this fifth number is going to contain 5 chickpeas. So I can quickly take them out and then start counting that there are going to be 5 chickpeas in my hand. Now even if I had million of these, and presumably I have like hands longer that can reach up to all of these million associates, I can very quickly find any number of chickpeas I want from this given example. So this would be a scenario where the time complexity is going to remain constant. Next one is logarithmic time complexity that we already saw an example using the sorted cards. And next we also saw an example of big O of n time complexity where the time increases linearly with the given input size. Now let's talk about big O of n square time complexity. Now for this n square time complexity, let's presume that we currently have these 2 decks present. What we are going to do is we are going to find a card from this deck, and this corresponds to, let's say, number 8. Now we are going to keep on scanning this deck until we find number 8. So we found number 8. That's great. Once again, we are going to repeat the same process, and this is going to be 3. So this one is 3. Once again, we found the match. Now this one is a joker, so let's just ignore that. This one is 7. So now for the 7, we will try to keep on shuffling through the deck until we find the appropriate 7. And in this case, it took us slightly longer, but we eventually find it. It's basically a matching between 2 separate decks. Now notice what is going to happen. For every single card that is currently present in this deck, worst case scenario, it could be possible that we might have to scan this entire deck before we can reach to that end conclusion. So for each of these n values, we will have to do n work. It's loop within a loop in order to find the established goal. And that is an example of big O of n square time complexity. Now for n cube time complexity, basically we are just going to have 3 set of decks where we will take value from one deck. Then we will try to find a matching pair from the second deck. Maybe it could take us as long as it takes. And then we will try to find another matching from the third deck. So this can take substantially longer, but overall this is what n cube time complexity means. It's once again loop within a loop within a loop. Now let's talk about some really large time complexities. So first one comes to mind is 2 to the power n time complexity. 2 to the power n complexity means that if you have an input that increases, the time it takes for you to generate the output multiplies by 2 every single time. And what is an example of that? Let's say that we currently have a coin.
احصل على كل ما تحتاجه للنجاح عبر الإنترنت مع عروض الجمعة البيضاء من هوستنجر. تبدأ خطة استضافة المواقع الآن من $2.49 فقط في الشهر. ابدأ عبر الإنترنت في دقائق مع هوستنجر AI، بالإضافة إلى الحصول على اسم دومين وشهور إضافية مجانا. احصل على دعم الخبراء في أي وقت وجربه دون مخاطر مع ضمان استرداد رسوم التسجيل لمدة 30 يوما. انضم إلى أكثر من 4 ملايين شخص يحققون أحلامهم عبر الإنترنت. انتقل إلى hostinger.ae وأطلق موقعك الإلكتروني من اليوم.
چۆنە کۆفێللا خۆشە کۆفێل
لەگەڵ خواردنەوەی کەپۆچینۆی کۆفێللا ئەس بەو پەڕی شارەزای تێکەڵکردنی شیر و شەکر و قاوەکەی بکە قاوەیەک پڕ لە تام و بۆن و هەستی ئیتاڵی.
Now this particular coin only has two possibilities. If I flip it, it can either be heads or it can be tails. That's it. But the thing is, what if I add one more coin into the mix? Now the number of possibility are multiplied by 2 again, because we can have 2 heads, we can have 1 head and 1 tail, we can have 1 head and another tail, or we could have 2 tails. So in this case we have 4 possibilities. If we add one more coin, the possibility once again multiplies by 2. We could have 8 possibilities. If we have one more coin, it once again multiplies by 2. We could have 16 combinations of heads and tails. If I add one more coin, the possibility multiplies by 2 again. So we could have 32 combinations. So notice that when we started merely with just 2 possibilities of flipping a coin, it has very quickly grown to 32 possibilities just with the addition of 4 input values. If I keep on adding the input values like 10, it's going to be 1024 and so on and so forth. So it's going to become very large very quickly, and these are the time complexities that we are typically trying to avoid, or it becomes very tricky to work with them. So do you think that this would be the worst time complexity? Well, you might be mistaken. There is also some more time complexities that are more complex than this, and that could be in the factorial time. So what does factorial time? Let's try to understand it with a simple example. Let's say that we currently have these 3 cards. Treat it as like 3 seats in a bus or an aeroplane or a movie theater. And then we have 3 friends who are currently trying to have a seat on these 3 different places. What are the different combinations we can have them seat in these places? Well, in the first seat, potentially all 3 can sit. That's very fair. Now, amongst all 3 can sit, if one sits, then for the second seat, the number of possibilities are 2. And for the third seat, the number of possibility is 1. So if we have to quantify that what are all the different permutations and combinations, there are 3 possibilities that can have a seat on the first position, there are 2 possibilities on the second position, and there is 1 possibility on the last position, and it's a multiplication of them because it's permutations and combinations of all the different people trying to have a seat on the first, on the second, and on the third. So it's going to be 3 multiplied by 2 multiplied by 1. So in total we can have 6 possibilities. If I add one more card into the mix, and if I add one more person, now the whole dynamics change, because on the first position potentially all 4 people can sit, on the second position potentially 3 remaining people can sit, 2 and then 1. If we do the multiplication, it comes up to 24. If I have one more card, and once again if I am trying to have one more person have a seat over here, now it becomes even more complicated, because on the first position any of these 5 people can sit. So it's 5 possibilities, then 4, then 3, then 2, and then 1. So it's a multiplication of all of these, and this comes up to 120. If I add 6 value, it's 720. So notice that how quickly the number grew from just having 6 for the 3 time complexity to having 120 possibilities for the remaining 2. So this is how exponentially the time complexity grows for a problem that involves factorial time complexities. Now there are some real cases where we actually do deal in factorial time cases, and we try to improve upon them using dynamic programming, and we are going to see a lot of examples of that. Now let's try to understand that why do we use the terminology big O to define time complexity or space complexity. Whenever we are defining the speed of an algorithm, we would say that it runs in order of the growth rate based off of given input size. What I'm trying to say is that if my current input is 10, it runs in let's say 10 seconds, and if my given input turns to 1000, it runs into 1000 seconds. So we can say that there is a linear connection between the input size and the time it takes to execute the algorithm. So we can say that this algorithm runs in the order of n time. So that's why the O in the big O refers to as the order of whatever the component it is that defines the growth rate. So we are trying to calculate the upper bound of growth rate for the given algorithm, and that's why we use the terminology big order of whatever the input size it relates to. Now, I know that you must be getting confused that about all of these different terminologies and big O of n and big O of 2 to the power n and n square and whatnot. So let's try to see very small, brief code blocks that I'm going to explain one by one, and then we will try to see that why we call it as whatever time complexity it is made off of. And that way it will clear some concepts for you, at least at the basic level. And don't worry if you don't understand some terminology, it would be covered throughout this course, so just stay with me. So now we are going to be seeing bunch of examples of different big O. So we will see different code blocks like this, and we'll try to figure out that what is going to be the big O for this particular code block and why that is the case. In the very end, we are going to see that for each of different time complexities, what does the impact or the growth rate is for that particular type of time complexity. So that would really put the things into the perspective that why these numbers matter so much. So let's try to understand this very simple code block. Basically, we have a very simple method that is called get first element, that takes in an array as an input, and it just simply returns the very first element present inside the array. Now,
Teenagers are building businesses with AI, while the only AI you know is ChatGPT. Let's be real. Most people over 40 use ChatGPT like it's Google. Copy, paste, ask a basic question, move on. That's not how smart people use AI. Tomorrow, we're starting the 28-day AI challenge for beginners over 40. Just 15 minutes a day to level up. In 1 week, you'll feel unstoppable. In 2 weeks, you'll have your strategy. In a month, you'll wonder why you didn't start sooner. Tap the screen to join us.
we know that if we are given an array like this, it's only going to take like x amount of constant amount of work in order to fetch the values, even if it's an array of size 5 or if an array of size 5000 or 5 million, it's always going to remain the same amount of time it takes to run this code. So we can call this as big O of 1 or constant time complexity for this code block. So this is a very simple example of that. Now let's try to understand more nuanced example. So in this case, we are basically doing a binary search. Now, if you are not familiar with this term, don't worry about it. This is basically the same stuff we did with the sorted cards we had, where we were finding the middle card, and then based off of that, we were either eliminating like one side of the cards or we were eliminating the other side of the cards, and then we were doing some other work. This is exactly the same stuff. The idea is that we simply go in, we fetch a mid value, and for that mid value we check that if the given target value, if that is equal to mid, we return it. If that is not equal to it, we either check the left side of the array or right side of the array, and then we simply return the answer. So basically we are running this code in big O of logarithmic time, log n time, and that is what this is an example of. Same way for this particular code base, if you check, we are doing a linear search. Basically, we are given an array, so that contains bunch of different values present within an array, and a target value we are trying to find from this given value. Now we don't know, target can be at this location, or at the very last location, and in the worst case scenario we might have to iterate over the entire array before we find the appropriate value. That is what we are doing. So we are running a loop through this given array, and then we are trying to find the appropriate value, and then we can return its position basically. So in this case we can say that this is going to run in big O of n time or a linear time, because basically if we have 1 million input, then it might take us like 1 million more times compared to if we only had just one input or two inputs. Now let's try to see this example. This is basically a very popular algorithm that we will be using quite a lot in a lot of the lead code problems. all it is doing is basically it's merge sort. So if the idea is that we are given bunch of different random numbers, they are currently present in any form, but once we run this entire algorithm, basically we would have a sorted array where all the values are going to be sorted in ascending or descending order depending on how we structure that. The idea is that we first take this unstructured value, we take each individual value, and then we start putting that within the given array, and based off of the value coming in, we will appropriately adjust our remaining values. So if the first value is 5, currently the array is empty, so we would simply just put 5 wherever, so in the first position. Next value is 3, so we know that the 3 is the smallest value compared to the 5. So in this case we are going to have the new iteration where again this happened where we did the middle value swap or basically binary search, and we were able to come up with the result like 3 and 5. Then we had the value 1, so once again we would repeat the same process and we would have 1 over here. Once again we would repeat the same process and eventually we would have 1, 2, 3 and 5. The idea is for each of the value over here, find an appropriate value to add in this new array, but this new array is always going to be empty and then it is going to be sorted. So we are going to be doing binary search over here. So for each of these characters, because we are doing binary search on all of them, basically we are doing n work, and then for each of this n we are doing binary search, that is log n work. So this code block is an example of big O of n log n work, and this is like you will see a lot of examples where we are multiplying the time complexities, we are adding the time complexities, so on and so forth. So again you would be able to figure it out, so don't worry about it. Now notice that this one is slightly different. Basically we are trying to find like the result of pairs within this given array. So what we are doing is we are running a for loop, and for each of the value within that for loop we are also running another for loop, and then we are just simply printing the pairs or the results of the value. But because we are doing like the combination of each of the value with its other subsequent parts, basically we are doing big O of n multiplied by n work. So for each individual items, repeat this n times. That is what this code block is basically doing. So we can call this big O of n square time complexity. Now big O of n square, if we take it like a notch further, this is like a for loop. So we have ith value, then for each of the ith value we have the jth value, and for each of the jth value we have the kth value, and we are simply repeating like a triplet pair.
What I admire most about Grammarly is that you're still in control of the writing. It'll generate a handful of topics in seconds, completely for free. As a reminder, we're not using this to write our paper for us, but it's simply giving us thought starters. I like this first one right here, so let's go ahead and choose that. And then the next step is finding sources, but that can get very time consuming. Thankfully, Grammarly can even summarize articles, so we can extract the main points and weave them into our writing with ease. It'll never write your essay for you, but rather steer you on the right path and polish your ideas. For example, with Grammarly Pro, we can rewrite run-on sentences to make them more clear, and we can also replace overused words so we don't sound repetitive. And if you're worried about using AI in school, there's a plagiarism and AI detector as well. They even have Grammarly authorship, which helps shows how much of your essay is AI typed, human written, or AI assisted, so you can have a transparent conversation with your professors. Grammarly is a must-have for all students.
For this one. So this is just an extension of the previous code block we had, where we have a loop within a loop within a loop. So for each n we are doing n work, and for each of that we are also doing an n work. So basically this is going to be big O of n cube. Now let's do some examples of really large time complexities, and this is where we are trying to calculate the Fibonacci of this given through this given code block, and we are doing some recursive calls back to the same function. Now let's try to understand that what this code block is doing. Basically we are taking in a value n. We are checking that if this value n is 1, then we simply return whatever the value of n is, which is 1 or 0. And if that is not the case, then we are calling this Fibonacci function again for n minus 1 value, and we are calling this Fibonacci function again for n minus 2 value. Let's see that how this is going to go. So basically, let's say that we have n is equal to 4 and we are trying to calculate the result for this. Now 4 is definitely not 1, so this condition would not work. So we will have to go over here where we are going to be calling the same function, Fibonacci function, for the value 3 and for the value 2. Okay, and we are going to be doing summation of these two. Now for this Fibonacci of 3, we are going to call this function again with Fibonacci of 2 and Fibonacci of 1. Now Fibonacci of 1, we already know that this value is 1, so that's good, we already have one result. Now for Fibonacci of 2, once again we are going to call it with Fibonacci of 1 and Fibonacci of 0. But for Fibonacci of 0, we know the value is going to be 0, and Fibonacci of 1, the value is going to be 1. So now we have this 1 and 0, so combination of these two is going to be 1. So now we have this 1. So now 1 plus 1, we have this value as 2. So now this value we received as 2. Okay, and now we also have Fibonacci of 2. So Fibonacci of 2 is once again going to be the value 1, and once again this is going to be basically 0. So this is also going to be 1. So the sum of this is going to be 3. So this is the answer we are going to return. But notice that instead of this being 4, if we had value as being 5, so this whole stuff would basically increase. Now we are going to be calculating for 4 and for 3. And for 4 we would be repeating all of these things, and for 3 we would be repeating all of these things. So it grows very large because we are going to have a very large calculation over here and very large calculation over here. If this value were to be 100, then once again we would be calculating for 99 and 98, and we will keep on repeating, so on and so forth. So this is a highly inefficient solution for a very legitimate problem, and the input size doubles every time, because notice that for this each number we are essentially calculating or repeating the multiplication of same calculation again and again. So this is an example of big O of 2 to the power n time complexity, where with each size or each increase in n, the time it takes for us to calculate this result doubles. So this is a very expensive time complexity. And now we have one more that is even more expensive, and this is an example of basically a factorial time complexity. So let's see that why this one is a factorial. Basically we are trying to calculate all the different permutations and combinations possible between given string as str and given string an answer. And now what we are going to do is we are checking that if this is 0, then we can simply return the answer. But if that is not the case, for every single character present in str, we are going to compare that with every single remaining value within this substring of answer. So this is going to become like very large very quickly, and that's why this is a factorial based time complexity. So this is like the most expensive one. Now let's try to put things into perspective, and we will see that how things change from like basically big O of 1 to all the way to big O of n factorial. Okay, so let's say that if we have big O of 1 time complexity, we are going to run a comparison table where we are going to compare the value of if given input size is 10, if it is 100, and if it is 1000, and we are checking that this is basically the time it takes to run the algorithm. Now for simplicity's perspective, let's just make sure that they are all of these numbers are in second, so we can have some way to comprehend or understand the results. For constant time, even if we had 10 results, 100 results, or 1000 results, it's always going to take us 1 second to calculate the result, because that's what it is, a constant time complexity. But for logarithmic n, with the increase in the size of n, there would be an increase in the time it takes to compute. But notice that for 10, basically 10 inputs, it would take us 3 seconds to compute. For 100, it would take us 6 seconds. For 1000, it would take us 10 seconds. So not a substantial increase. Meanwhile, our input actually like increased 3 folds. So 10 multiplied by 10 multiplied by 10. For n, it's linear, so 10, 100, and 1000. For n log n, it basically takes us like multiplication of these two. So 33 seconds, 664 seconds, or 9000 something seconds. For n square and n cube, it's essentially just the square value of all of this 100, 1000, and 10,000. And notice that how large it gets, especially for like n square time complexities or n cube time complexities. that the number keeps on growing larger and larger. So this is a good cue to ourselves that if we have n cube, can we bring it down to n square? If we have n square, can we bring it down to n or n log n, something like that? So the better we can do in this regard, the faster our algorithm is going to be. And for 2 to the power n and n factorial, the numbers are just out of this world. Like even for 10 input sizes, it takes us 1000 seconds to solve the problem in 2 to the power n. For n factorial, it takes us like 3.6 million seconds just for 10 inputs. And for these, this is like 10 to the power 30 and 10 to the power 301, which is like huge numbers. And these numbers are even larger than that. So uh, we should always try to avoid these time complexities no matter what. And there are some ways of doing it using like dynamic programming and greedy approach and being creative about different things. So we are going to be learning that throughout this course. Just this is just something to keep in mind. Now let's try to understand that what is space complexity. Once again, space complexity is denoted by big O notation, and it is the amount of space required in order for us to accomplish our expected goal. So let's try to understand it with a live scenario. Currently, I have two containers. This container contains bunch of different white chickpeas, and it is a white container. And I have a black container that contains bunch of different black chickpeas in a black container. Now my aim is to move all of these black chickpeas into this white container and move all of these white chickpeas into this black container. How would I do that? If I only had these two containers available, and if I have to do one by one, what is going to be the algorithm that sequentially or individually I'm going to pick and choose all of these black chickpeas from this one and keep on adding them, and then at the same time I'm going to be adding the white chickpeas over here. Again, it's going to become extremely excruciatingly difficult because there are so many chickpeas that looks pretty much the same, and it's going to take me a lot of time to do it. But if I add the space complexity, or if I add one more container in between, if I just move all of these black chickpeas like this, all of these white chickpeas like this, and once again all of these black chickpeas like this, notice how quickly I was able to flip between the all the chickpeas amongst these two containers because I had to use this extra container, and how quickly this whole algorithm was able to be finished because I'm no longer doing any kind of addition or subtraction in this case. And that is how powerful space complexity can be. Many times we are going to be seeing that if a problem is going into the realm of big O of 2 to the power n time complexity or factorial time complexity or even n square time complexity, we might use an extra data structure to store the previously computed results, and that is going to allow us to very quickly flip between our inputs and retrieve the answer very fast, and we will be able to solve problems much quicker. And that is the whole idea of space complexity. Once again, it gets denoted by big O, and we are going to learn a lot about them in each of the LeetCode problems we are going to solve.
Kia, movement that inspires.
Now let's talk about the million-dollar question. How do you even get good at DSA? Now, number one thing is practice. Second thing is to be able to understand all the different data structures and all the different techniques we have, and then try to look for important patterns that repeats in many cases, which we are going to be doing through lots and lots of interview examples and understanding different patterns. And third thing, you need to follow the simplest strategy of understanding the problem in the most basic terms as a non-IT, non-computer graduate person would do. Just try to think that how does a simple problem that is being thrown at you, how would you try to understand it in your own words, build some basic examples, and try to solve it using the most simplest terms or even the brute force approach, even if it is not optimized for speed or anything else. Next, you will try to see if applying different data structures in any particular questions you are given, can they be helpful in speeding up some repetitive process. And number three thing, if you have a brute force solution that has, let's say, big O of n cube time complexity, your immediate aim should be to make it better than big O of n cube. Can you make it like big O of n square? Can you make it big O of n? Can you make it log n? So on and so forth. So once understand the problem in the most basic terms, come to the most basic, most rudimentary solution, and then see if you can improve upon that. And whenever you are doing this throughout, keep your interviewer engaged in the conversation communication. Just let him know that, hey, this is what you are thinking, this is what you are doing. Just be as transparent as you want. They are judging you based off of, do you have like proper communication skills and problem solving abilities, and how does your thinking works. If they see that you are tackling a problem that you have never seen before, and you are building like a brute force solution, and then you are correcting yourself, and then you are making a better solution, and if your thinking is correct, there is a very high likelihood of you being selected for that next interview or for that next job. So that is what we are going to learn. So now let's move on to the next topic. So let's try to understand that what is the classification of different data structures. We can broadly divide data structures into three main categories: linear data structure, non-linear data structure, and hash-based data structure. So let's try to understand each one of them. A linear data structure is a data structure where basically all the elements are typically sequential. So it comes into the data structure one after the another. Think of it, all the elements being present in some sort of a line. So what are the linear data structures? First one is an array. Array is a fixed size linear data structure that we are going to see a lot of examples of. Basically, in the memory of the computer, we allocate a fixed size block where we can enter elements and where we can remove elements. And all the elements are going to be accessed by the index position of that particular element. Next one is a linked list. Linked list is completely different compared to array, where we don't have a fixed size. So basically it's a dynamic data structure. And for this dynamic data structure, we can basically have two items. We have the head of the linked list and we have the tail of the linked list, or the last element inside the linked list. Now head of the linked list points to what is going to be the very first element inside the linked list. And in this very first element, basically this element is made out of two chunks in the memory. First one contains whatever the value this linked list persists, so it can be integer, boolean, whatever you want to imagine. And in the remaining portion, it shows that what is going to be the address of the next element inside the linked list. And next element is also formed similarly, next element is also formed similarly. And the last element, that is going to be the tail of the linked list, this refers to, or this points to the null variable or null pointer, and that's where the linked list ends. So basically linked list can shrink and grow in the size depending on how many elements are there, and it can all happen dynamically, so we don't have to worry about it. Now stack and queue, they both can be formed using arrays or using linked list. Basically these two contain some special properties. So stack is a kind of last in first out data structure, where you can imagine this as being stack of plates or stack of books, where if you have to access the books, you basically put books from bottom all the way to top. But when you want to get any book out, first you have to get the top book out before you can reach to the next book. So it's always going to follow this property, and this can become helpful in a lot of different scenarios, and this is an example of stack. Now queue is again a complete different or opposite concept of stack. A queue is typically the queue that we typically follow in any place like bank or movie theater or anywhere, where we follow first in first out principle. So let's say that if this is the queue and we are entering from this end and we are exiting from this end, so basically whichever the element was the first to come in the queue is also going to be the first to get out of the queue. So this is separate compared to our stack example, but basically both stack and queue also follow the linear property, where one element comes in after another element, and that element comes in after another element in some fashion. So basically this is an example of linear data structure. Now let's try to understand non-linear data structure. Now a non-linear data structure is a data structure where we don't have any sort of sequential line or sequential property that we need to follow. Basically elements that are present inside non-linear data structure, they typically follow some sort of hierarchical data structure, or they follow some kind of networking related data structure, where one element can come in after another element, that comes in before some other element, that comes in after some other element. There can be all the different kinds of jumbled up relationship, and we need to follow that. And some elements are not attached to the existing set, but they're still part of the given data structure. So this is an example where this is going to be dynamic data structure, that's for sure, because it can grow and shrink in size. And there are many different ways to implementing that we would see later in subsequent courses. But overall, there are two main non-linear data structures. First one is graph, and second one is a subset of graph that is defined as trees. So let's first talk about trees, because this is like kind of slightly smaller compared to graphs. Tree is not your typical tree. This is a different kind of tree where we have a root variable. So this root variable is going to be the entry point into the tree, and from there it can have sub children, or it can have children of its own. And there can be many different type of trees. There can be binary trees, ternary trees, AND trees, unique trees, red and black trees. So there are many different concepts, but overall the principle is that each element is going to be differentiated based off of its level. So all the elements that are currently present at the bottom level, these are referred to as leaf node because they don't have kids of their own, and all the elements above leaf are going to be the parents of that subsequent level. So these nodes are going to be parents of these nodes. Once again, this root node is going to be parent of these nodes. So overall, we follow some sort of hierarchical property when we are talking about trees, and it can be useful in many different scenarios, and that we will see for sure. Now, one thing important in the tree is that all the nodes are connected. So we don't have a scenario where there can be a node of tree that is part of this tree but not connected in some sort of edge. So it is always going to be connected somewhere along the tree, and also there cannot be any cycles. So all the nodes are going to be uniquely defined, and there cannot be cycles present inside a tree. So these are the two main things that differentiates trees from the graphs. Now let's talk about graphs. So in the graph, basically we have two things. We have nodes and we have edges. And these nodes and edges have some sort of connection between them. So there can be two nodes where it's possible that only one node has edge going from one place to another one, but other one does not. Some places both of them have edge going towards each other, so we can define it as two separate edges. There can be a connected graph. So this is an example of connected graph where all the elements are connected with each other. There can be non-connected graphs as well, where some nodes are connected and other nodes are not connected. Some clusters can be connected and whatnot. So there are many different examples of graphs as well. There are directed graphs, non-directed graphs, there are weighted graphs, there are unweighted graphs, cyclic graphs, non-cyclic graphs, and so on and so forth. And we can do all sorts of things using graphs. It can be used very heavily in applications such as social networks, where you have a bunch of different people who have some sort of relationship with each other. So someone is friends with someone else, someone is following someone else, and you need to define that. It can also be very helpful in defining some sort of maps where you have a bunch of different places or cities, and then there are roads going between those cities. So how you can connect that, how you can find the shortest path and things like that. So again, graphs is also very powerful and very useful in a lot of different cases. And last data structure we have is going to be hash based. Now inside the hash based data structure, we have some sort of hash that defines every single element that is currently present within the hash map or hash set in very quick manner. So we can identify and pick out elements very quickly in basically near constant time. So why this is useful? Because if we talk about some data structure, let's say array or trees or anything, if we have to find any particular element, worst case scenario, we might have to iterate over entire array or entire tree before we can find that element. But if we have a hash map or hash set, we can virtually find that element in big O of one time. And why this works? Well, basically, let's first try to understand hash map. So in the hash map, we have something called key value pairs. So anything or any value that we try to insert within the hash map is going to have two elements, a key associated with that and then a value associated with that. Let's try to understand a very simple and basic key. So we will try to determine that what is going to be the starting alphabet of any particular character. So let's say if element starts with A, we are going to define key as A and then add the value as apple. And for simplicity, we are making sure that we can only have values from A to Z and each are going to have just one unique value. So same way for B, we can have a value for ball and whatever and whatnot. Now, if I am trying to determine that whether bat is currently present inside this hash map or not, I don't need to scan all 26 values that are present. I can very quickly go to this element where the B is present and check that what is the value associated with that. And currently, because this value is ball and it's not bat, I know for a fact that bat is not present. So I can return this answer very quickly. This is the advantage of hash map. Now it could be possible that if we just have one key and we want to add multiple value, we can put some sort of linked list over here, but there are going to be advanced concepts that we can think about it. For simplicity, let's try to understand that we have some sort of mathematical formula that uniquely defines any single element within the hash map. So for each key, like in theory, we only have one value associated. If that's the scenario, no matter if we add million keys over here, basically we can find any particular value in very quick time and very quick fashion. What are some of the downsides? Well, we cannot have duplicates values because all the duplicate values are always going to end up within the same key value pair. So we can't have duplicate values being inserted within a hash map, and that is also true for hash set. Now the difference between hash map and hash set is that again for all the elements that are present in the hash set, they also get stored, but we don't store any particular key for them. We only store the value, and we can check that whether this value is currently present inside the hash set or not, or we can add the value inside the hash map, and all the operations are very quick. They happen in virtually big O of one time, but again there are differences and some trade-offs we will have to make sure if we are working with hash map or hash set, and we are going to be seeing plenty of examples of these as well throughout the courses, so don't worry about it if you don't understand. So I hope this all makes sense to you, and now you have some clear understanding that what each of these data structure means. So now let's try to do a quick recap. We first understood that what is data structure and what is algorithm. Then we understood that how to judge an algorithm, what is time and space complexity. Then we understood that what are the different categories of different data structures. And now we will start getting into the meat of the actual course. So we are going to go with the 20 topics that I discussed earlier. For each of the topic, we will understand that what that topic is, what are the different common operations, patterns, use cases associated with that topic, and then we will start solving most tasks, most like and most popular lead code problems or technical interview problems associated with that problem. That is how you get good at solving technical interviews and building your intuition for solving the problem. So I know it's not going to be easy. It's definitely not going to be entertaining. It's going to be very boring in some cases, but you just have to have the perseverance, because if you go through this whole process and actually become better at your technical interviews, you can change your lifestyle within 3 to 6 months. Like completely different compensation, completely different bracket, different country, different company, whatever. So motivations are huge, benefits are tremendous, and it's just a long journey that you have to endure. So I wish you best of luck. Now, if you made until this part of the video, just comment the word pineapple, because I like pineapple. I hope you also like pineapple. Who doesn't? And without any delay, let's get started. Hello friends, hope you are having a fantastic day today. So now we are going to learn an entire full course on array as a data structure. By the end of this course, you should be an expert in all the questions related to arrays. First, let's try to understand that what an array is. Array is nothing but a continuous block of memory that is currently stored inside your computer. Now inside this continuous block of memory you can store integer data type or boolean data type or string, character, whatever you want to put. You can store these values, but arrays have some restrictions and some properties. Number one restriction in an array is that it is a fixed type of data structure. So whenever you are storing the information, you need to define that what is going to be the size of this array. So currently this array that I have provisioned can only hold up to 5 distinct values. Second thing is, everything inside the array is defined by its index positions. So in this case, for this array, the index values would be defined as 0, 1, 2, 3 and 4. On top of it, because this is a fixed size and also all the values are continuous in nature, I can fetch any particular index position values in constant time. One of the other thing is computer knows that what is going to be the memory size for each of these blocks. So let's say that this block cost 8 bytes of memory to be stored inside the computer. Also, computer knows the starting position of this particular memory location. So let's say that inside the memory of computer, this one is defined by 1600. So logically, if we have to access this value, the position is going to start from 1608. Same way, position for this is going to start from 1616 and so on and so forth. So that's why this makes array unique and fast in terms of nature. Now let's learn that what are the different array operations that we can perform and also what are going to be its time complexities. So first operation that we would like to see is access. That let's say that if there is some element that resides at position number 2 or position number 3, how quickly can we access? We just explained that this can be done in big O of 1 time and fetch the value that we are looking for. For the insertion, typically in normal scenario this works in big O of 1 time, but worst case time complexity can be big O of n, because we are trying to find a space where we need to insert the value. So if it is a random insert that we don't know that whether we have an empty space or not, or if we are trying to make frequent modifications, we might have to shift values inside the arrays as well. Same goes for the deletion, that because we are deleting some elements from the array, we will have to shift the cells here and there. So in that case, worst case scenario, it can be big O of n, but typically most of the languages handle these scenarios in relatively simple fashion, and average scenario is going to be big O of 1 for both of them. Now traversing an array is very straightforward. You simply start from the starting pointer and keep going in one direction until you reach to the very end of the size of the array, and this can typically be done in big O of n time, where n is the total number of elements present, because you will have to iterate over every single element in order to access them. Searching is also quite an interesting one. Let's say that currently this array contains 5 different elements, and you're trying to search that whether any particular element resides inside this one or not. Let's say that you are trying to see that whether element number z is present or not. So in this case, if these values are not sorted and these are random values, then you must do a linear search. And a linear search is only going to yield big O of n result, because you will have to reach or search every single value. Or you can do something called a binary search if the given values are sorted. So you can see in this case the given values are sorted lexicographically, so we can actually apply binary search in this case, and we can solve this problem in big O of log n time. And don't worry about these things, you are going to see tons of examples of these things in action, so it would become a second nature to you. And last one is an update. So if you have to update any particular element, let's say that instead of this x, I want to update this value to be m. So I can do this instantly because I can reach or fetch that element. So number one benefit of an array is that we are dealing with random access time complexity of big O of 1. So if we have to access multiple values from the array, we can do it in big O of 1 fashion. That this is going to be really helpful in certain scenarios. Next thing is, array is a wonderful cache friendly data structure, which means you can see lot of different operations where array becomes a supporting data structure for the main problem we are trying to solve. We can use array very heavily in dynamic programming problems. We can use array with graphs, trees, and all the other data structures in order to store some valuable information that we are trying to memorize, or using it by tabulation. Next thing is, we can very easily sort values inside the array. And next thing is, array is very popular in implementing other data structure. You can implement heap, you can implement tree, you can implement linked list, you can implement stack, queue, all of these things using different ways to modify and manipulate arrays. So arrays are overall very diverse data structure. Now let's see some limitations. Number one is, because arrays are fixed size, there is only so much you can do. If you are dealing with some dynamic problem where the value are continuously increasing, and if you are trying to use array, then it becomes obsolete, because every time you are going to be facing an issue where array runs out of the size. So you can only use array until you know for sure that the size is going to be fixed. If you have to deal with dynamic scenarios, you can use something called array list, where inside the array list it helps with like dynamic nature, but there is a whole separate discussion on its own. Next thing is, for typical insertion and deletion, worst case scenario, it can go into big of n if you don't know where you are trying to insert those elements or delete those elements from. And next thing is that it is very inefficient in terms of frequent modifications. Now let's see that what are some of the common use cases where you should start think about using array for various different purposes. Number one use cases that I just explained is to implement other data structures, because array is simple and can be modified in many different ways. Next thing is, whenever you see any kind of caching or tabulation or memoization item that you need to perform, you must start to think about using an array. Third thing is, whenever you are dealing with graph problem or tree problem and you need to keep track of visited nodes, then you can also think about using an array. Then whenever you need to do some sort of mathematical computation, you can also use an array. And one good thing about array is that it has lot of popular coding patterns. So coding patterns such as two pointers, sliding window technique, then a fast and slow pointer, and all of these things can be used in many different ways that can become really helpful. And we are going to see all of these in action when we do our 25 most popular most asked questions. Now arrays also comes in multiple dimensions, not only one dimension. So far we have seen all the arrays that typically looks like this, where we can define this as one dimensional array, where you can notice that every single cell only is being defined by one particular index position. Now there can be scenarios where we need multiple categorizations to define any particular cell value, and for that we can actually use multi-dimensional array, where this is this would be an example of 2D array. Same way we can have a 3D array, we can have a 4D array. So let me give you a common scenario. Let's say that I just want to say that whether any particular student is present or not. So I can create an array like this, where I'm storing a boolean information, and in each of the scenario I am marking all of these values based on the student roll numbers or ID numbers. So this becomes a one-dimensional array problem that I can solve easily. But now I want to create a matrix of information such as grades for every single student, on top of it their roll number. So I want to define each of the cell based on their grade and roll number. So I can create one entire section of grades starting from A to F, and same way I can have another section for a roll number starting from 1 to 3 all the way up to n students. Now any particular cell in this position is going to define that this cell defines that for roll number 3 whether that student got B grade or not. So this can be another way of categorizing values, and this also contains the same property of fast access and all of the good stuff that array has to offer. So typically for any DSA problem and technical interviews, we are only going to be dealing with 2D arrays, but in theory and also in practice we see all the time 3D and 4D arrays as well. 5D arrays very rarely, but this is something to just understand. The lead code problem we are going to solve now is called toSum. This is the number one problem on the lead code, and we can see that this one is an easy problem and also the most like problem on lead code. Let's understand the statement. Basically, we are given an integer array nums and we are also given an integer called target. Now we need to return the indices of the two numbers within the nums array such that they are the sum of target. So basically they add up to the value target, and we are guaranteed that there is always going to be one solution, and we can return these indices in any order. So let's try to understand this with an example. We are given an input array nums over here, and we can notice the values are 15, 7, 2 and 11, and we are also given target value to be 9. Now in this example we can see that the 7 and 2 sums up to target value number 9. Now if we see the index positions of the 7 and 2, they are located at basically 1 and 2 position. So we can return the answer as 1 and 2, or we can also return 2 and 1, whichever like sequence we want, but basically this is what we need to return. Now let's understand that what are the different ways we can actually find the sum of these two values. So first let's understand the brute force approach. Basically for the same example, let's say the values we are given, we are going to try every single permutation and combination. So what we will do is, currently this value is 15 and the target we wants to make is 9. Okay, so this value is 15, so we cannot use any other value to basically form the target value as 9, so we can just ignore this case. Okay, now this value is 7. So because this value is 7, the total target we wants to build is 9. So what we'll do is we'll do 9 minus 7. So we will check that if the value 2 is present inside the remaining array or not. And lucky for us, the value 2 is present. So we can just return basically the index positions of these two. Now notice that in the brute force approach, what we are essentially doing is for every single character, in the worst case, we might have to iterate over all the remaining characters to see if any particular value is present or not. Let's take an example that if this value was to 1, then we would have to check that whether 8 is present. So for that we might have to basically go over all of them. So the time complexity would have been big O of n square. That is a bad time complexity. Now let's see that if there is any particular way we can improve upon that, and the answer is yes. If we do sorting, basically things would become slightly better and easier. How? Let's understand that for the same example, if the values are 15, 7, 2 and 11, once again if we sort these values, we would be left with value 2, 7, 11 and 15. Now we are at value number 2. Okay, so notice that if the target we want to generate is 9, if we already have value as 2, which means if we do 9 minus 2, the answer becomes 7. Now all we need to do is to check that whether 7 is present inside the remaining array or not, same as our brute force approach. But in this case, because we know that this is already sorted, instead of using linear search where we are iterating over all of these values one by one, we can use binary search, and that would help us alleviate a lot of questions. But because in the binary search, remember that we will find the middle value. So let's say we find middle value is 11 in this case, and from 11 we know the value we are trying to build is 7. So even if there were like 100 elements on the right of 11, they will all be greater than 7. So we cannot use them. So we will just ignore the entire right portion and only limit our search to the remaining piece, and we would be able to find the remaining value in essentially log n time, which is exceptionally fast. So this, if we see like the sorting approach of sorting the original input array, things becomes quicker, and we can actually solve this problem in big O of n log n time, and this is the time to basically sort the given input plus log n time to find any particular character. But the thing is, generically we can just write it big O of n log n as the overall solution. Now the question is there a way to do things quicker? And the answer is yes. We can even do things faster if we use an additional data structure in this case. And let's see what are the considerations for us to understand any particular data structure. Number one thing is, whenever we see a value, we are trying to basically determine that what is going to be the remainder. So in order to quickly look up that do we have that remainder or have we already passed that remainder or not, what we can do is we can use a hash map in this case. Now notice hash map contains two properties. First thing is a key, and second thing is an appropriate value. Now as part of the key we would put whatever the array item that we currently have. So let's say that we are given once again this array as an example. Okay, now in this case we once again need to return the target value of, let's say, 9. So now in this case what the algorithm we are going to use is, first we'll iterate over any particular character inside the given nums array. For that character we will see that what is the remainder value we are trying to generate. So for this value number 1, we know that the remainder value should be 8. The question is 8 present inside the hash map or not? If it is not present, that's it. We simply add this value 1, saying that it could be potentially a match for some future target value that we are trying to generate, and continuously we will keep on doing that. So as a key we will add value 1 over here, and as its appropriate value we are going to store the index position. So index position for this 1 is going to be 0, so we will store value 0 over here. Now let's repeat the same operation. Now next value is value number 7. So for if we already have a 7 to be part of the 2 sum that we are trying to generate, we will need to have 9 minus 7, which means value number 2 as part of the hash map. But currently hash map does not have value number 2. So what we'll do is we'll simply add value number 7 with its index position as 1. Same way we have value number 3. If 3 were to be part of the answer, we need to find value number 6. 6 is not present inside the hash map, so we will simply add 3 over here with its appropriate subsequent value, that is index position number 2. Now we are at value number 2. For 2 we need to find value number 7, and lucky for us 7 is present within this hash map, and we already know its subsequent value is 1. And since we are already at 2, we know the index position of 2 as well. So in this case we can return the answer as, let's say, 3 and 1, or we can also return like 1 and 3, whatever we want. But basically this is the index position of the values that basically sums up to total value number 9, and this is the fastest way to solve this problem. Now let's analyze the time and space complexity. Time complexity is going to be much faster big O of n. Why? Because we are iterating over all of these elements just once and we are coming up with the solution. Because remember, searching that whether any particular value is present inside the hash map or not happens in big O of one time, which is significantly faster than everything else. Let's analyze the space complexity. So space complexity is going to be big O of n as well, because we have to use an additional hash map to store the results. But needless to say, this is much quicker than both our brute force and also our sorting approach. So now let's see the coding approach for this one. So the coding solution is quite straightforward. First, we are going to initialize a hash map to store all the values and their index positions. Then we are going to iterate over the given input array nums. And for each of the array, we are going to calculate that what is the remainder value in a variable called complement. Then we are going to check that if that complement is already present inside the hash map or not, which we can do in big O of one time. If the value is present, we simply return a new array that contains the value of that particular key and the current ith position. These are the two index positions. If we do not find that value, we simply add this current number that we are iterating over within our hash map using map.put. And in the end, we simply return an empty array if no solution is found. But this wouldn't happen because in the problem we are already told that there is always going to be exactly one answer. We are just putting this return statement so we don't get into a compile time error. Okay, let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And we beat nearly 99% of all the other solutions, which is awesome. And in terms of memory usage, we can improve if we use some other solution, but this is also, needless to say, a very good time and space complexity, and this is the most popular problem, so you must know it by heart. Once again, the coding solution is present in our GitHub repository, so feel free to go and check it out from there. Thank you. So the lead code problem we are going to solve now is called contains duplicate. We can see that this one is a lead code easy problem and also an extremely well-liked problem. The statement is quite straightforward, that we are given an integer array called nums. Now we need to check that if there exists any particular value more than one times, at least twice, then we need to return true, saying that yes, there exist duplicates in the given array, and if it does not exist, we need to return false. So let's try to understand this with an example. Suppose this is the input array we are given. Now we can notice that value 4 appears twice in this case, which means there exist duplicates in this given input array nums. So we need to return true in this case. Now if, say for an example, we are given one more nums array and all the values are unique, or we don't see any duplicate values, so basically in this case we can return false, saying that there does not exist any duplicate values. And the statement is very simple to understand. Let's see that what is going to be the most common brute force approach we can use to solve this problem. We will take the first value and we would check against every single other value possible, that whether 1 is present or not. We identify that 1 is not present, so in this case now we would move on to the next value 2 and once again repeat the same operation. For 3, repeat the same operation, and at the 4 we would realize that there exists one value 4 that is being repeated. So basically found a duplicate, so we will return true in this case. And say for example, if we don't find duplicates and we reach to the end of the array, then we can simply return false, saying that there does not exist any duplicate values. Straight away you can see that what is the issue with this approach. Well, the idea is that for any particular n value or any particular work, we will have to repeat the same operation for every single other values, which means the time complexity is going to be big O of n square, which is definitely pretty expensive, and there are ways to make it faster. So the first optimal approach that comes to our mind is basically sorting. If we can somehow sort the given input array, then things would become much easier. Let's say that we are currently given an input nums and the values are scattered all across the place, and we can find that there are some duplicate values over here as well. If we sort this given input array, then the sorted input is going to look something very similar, and then for the sorted input, all we need to do is just keep checking all the values with its next value or previous value, and over here after 1 we find value number 3, which means it is not possible to have 1 in the remaining array because this is a sorted array. Same way for 3 we found value number 5, which means there is not possible to have another 3 inside the remaining array. But for 5, because there exists a duplicate, it has to be very next to it. We found a duplicate and we can simply return true in this case very easily. Now this is a much better approach than our brute force approach, but let's see that what is going to be the time complexity. Well, it is going to be big of n log n, because it takes n log n time to sort the given input array. And the question is there a way we can do something better? And the answer is yes. The fastest approach in this case is going to involve something where we need to keep track of all the elements that we have already seen, and we should be able to access them quickly. And these are the two basically conditions that we need to follow. And for that, the best data structure in this case is going to be a hash set, that it cannot contain duplicate values, and it basically finds any particular element inside the hash set in big O of one time. So suppose this is the array we are given as an input. Now what we will do is that we will iterate over this array, and for every single value, first we will check that whether this value is present inside the hash set or not. If it is not present, we will simply just add it to the hash set and it move to the next value and repeat the same process. So let's see that how would that work, and let's say that this is going to be our hash set. Okay, so first we are at value number 3. Currently value number 3 does not exist inside the hash set, so we will simply add value number 3 and move on to the next value. Once again value number 1 does not exist, so once again we would add value number 1. Now 4 also does not exist, and now once again we would move to value number 1. Again at value number 1 we would check that whether this exists inside the hash set or not, and yes, it does exist inside the hash set, and we can check that in big O of one time, which is awesome. So in this case we can say that because there exists a value that is already present inside the hash set that we are trying to add to the hash set, which means the given array contains duplicate. So in this case we can simply return true, and say for some reason this value 1 is not present over here, and let's say that this value is maybe 6. So 6 currently does not exist inside the hash set, so we will add 6 over here. Once again we are at value number 5. 5 also does not exist, so we will add 5 to the hash set, and now we have reached to the end of the array. So if we reach to the end of the array, we can simply return false, saying that there does not exist any value that is duplicated. If we see time complexity, in this case the time complexity is going to be big O of n. Why? Because we are simply iterating over the given input array once, and for every single value, even though we are checking that whether it's present inside the hash set or not, it can be done in big O of one time. That is the power of hashing functions like hash set and hash map. And if we see space complexity is going to be big O of n as well, because we will have to use one more hash set to store all of these variables. But still, this is much better compared to our brute force approach that had the time complexity of basically big O of n square. So now let's see the coding solution for this one. So the coding solution is going to be quite straightforward. First of all, we are going to initialize our hash set that we are going to keep track of the scene numbers. Then we are going to iterate over every single element that is present inside the nums array. And for each of those elements, we are going to check that if our hash set contains that particular number or not. If it does contain, then we can simply return true, saying that we have detected a duplicate. If it does not contain that number already, then we will just simply add that number. Say for an example, if we end up iterating over every single element in the array and we reach to the end of the array, which means there are no duplicates, so we can simply return false. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And as expected, code runs beautifully. It beats nearly 90% of all the other solutions that are present on the LeetCode, which is pretty awesome. And the solution of this code is present in our GitHub repository, so feel free to go and check it out from there. Thank you. Okay, so as an example, we are trying to solve the contains duplicate to problem. Now, this is a very popular LeetCode problem that has been asked in some of the popular companies like Amazon, Facebook, Adobe, Microsoft, Uber, Google, Bloomberg, Airbnb, and Plantier. So these are all tech giant companies who love asking this question. So that is why I considered this one. Let's try to see the problem statement. The problem statement is actually quite simple, and this is a LeetCode easy problem and also a very well-liked problem on LeetCode. Basically, we are given an integer array called nums, or we are going to denote it as n, that contains array values. We are also given a value k, and k can be anything like 1, 2, 3, 4, any single integer value. So suppose k is equal to 3. Now we need to return true if there are two possibilities. The first possibility is there exist any two values I and j that are exactly same. So if there exist two duplicate values in the array. And the second portion is that the difference between I and j, so I and j refers to the index positions of every single value inside the given array. So the index position should be actually less than the value of k. Let's try to understand this with few examples. So suppose our given input n is equal to 1, 2, 3, 1, 5. If this is the input we are given, and we are given the k value to be 4. If this is the case, does it satisfies these two properties? So first let's see. Okay, so we need to check that between the window 4 there needs to be two duplicate values. Currently we can see that there exists a duplicate value 1 and 1 over here. Let's see the index position 0 and 3. So if we do the difference 0 minus 3, so basically we need to do the absolute difference, so the answer is going to be 3. 3 is actually less than the value of 4, which means this one currently contains the duplicate value that is not far away from 4 elements from each other. So in this case, we are going to return true. Let's try to understand it with one more example. Suppose our given n is equal to 1, 2, 3, 1, 0, something like this. And our given k value is equal to 2. If this is the case, again, same scenario. We have the values located at index position 0 and index position 3 that contains the same value. But current k value is equal to 2. And if we do the difference between these two values, the current difference between indices is 3. Meanwhile, our given k is equal to 2, which means in this case, we need to return false because there does not exist any two duplicated values that are 2 steps away from each other or between two elements of each other. So this is the whole ask. Now let's see that what is going to be the simplest approach we can take. Okay, so suppose this is the input we are given. Now let's see the brute force way to solve this problem. That we pick any element, then we check the next k elements. So in this case, currently we are allowed to check up until this point. So between these portions, we check that whether 0 is present in any other value or not. If 0 is not present, we can define that 0 would not be a duplicated entry in any of the window, because we are strictly told that we can only check next 3 elements. So in this case, we can get rid of 0 because 0 is not present. Same way, we are going to check for value number 5. So currently value number 5 is located at index number 1, which means we have the ability to compare between these portions. So again, for value number 5, we are going to check this value, and this value, and bingo, we find value number 5. So we can return true in this case because element number 5 exists and the difference is less than 3. But this is like a very inefficient approach. Why inefficient approach? Say for an example, this entry does not contain any duplicated values and all the values are unique, and at the same time what we would do is, for every single element we would compare it with the next 3 elements, and we would keep on repeating the same process until we reach to the end of our loop. And that would be an inefficient approach because the time complexity would be big O of n. So n is the total number of elements multiplied by k, and this is not what we want. We want something more efficient. So let's see a more efficient and better approach. A better approach is that we know that for any single value, we need to check in the remaining portion whether that value is present or not. So currently we can break it down in this sequence. So currently we can create a window like this, 0 and then 5 2 7. Currently we are at this position number 0. Now we need to check that whether 0 exists in the remaining 3 entries or not. First approach is to do binary search. So for binary search, what we would need to do is we would need to sort this given input. And if we sort this input array, the sorted result is going to look like this: 0, 2, 5, and 7. And then all we need to do is check any 2 consecutive values. If we identify that there exists like a back-to-back entries that contains the same value, then we can return true. If it does not contain, then we can move on to the next window. And again, in the same way, we would repeat the same process for this next window that is currently comprised of the values 5, 2, 7, and 3. And again, okay, so let me fix this one. So this one should be 5, not 7, and 5, 2, 5, 3. So again, if we sort this window in this case, the answer we are going to get is 2, 3, 5, 5, and we found 2 back-to-back values that contains the same value. So in this case, we can return true. But the thing is, even this approach is also not very efficient because if we see time complexity in this case, the time complexity is going to be big O of n, then log of k. Why log of k? Because for any given input, we will actually have to sort this, and sorting it cost us a lot of time and energy. And this is better than the brute force approach, but still there can be improvements made. So what is one improvement we can make? And again, remember, we are using sliding window because we know that we need to do this in any subsequent values and we need to find the answer. So definitely you understand by seeing the problem that why we need to use the sliding window. But let's see that what would be the improvement we can make. First thing we need to check is that in the binary search approach, what we had to do is we need to check that whether in the remaining portion does the same element exist or not. And also at the same time, we were considering that every single time we need to create a new window, we would have to do the entire sorting calculation again. So we need a data structure that can very quickly get rid of elements and add new elements, at the same time very quickly search that whether the existing element exists or not. And the wonderful answer for this type of scenario is a hash map. So we can create like a hash map or a hash set inside our input, and hash map and hash set are wonderful at doing 2 things, like doing the search and remove and input operations in big O of one time. So hashing is really good in that. Also at the same time, it does not allow duplicate entries. So no duplication is allowed, which means we can identify duplicate entries very quickly, very efficiently in any sort of hashing input. So we are going to use this property combined with sliding window approach to solve this problem in the most efficient manner. Let me quickly show you. So first we are given the value of k, which means we are going to create our window. So currently let's just create a window of size k. Okay, so starting from value number 0 to value number 5, and then we will have all the values 0, 5, 2, and okay, let me just put down some different value over here, and let me put 5 over here. Okay, and then this is going to be 4. Okay, so this is these are the current values at the moment. We are going to initialize a hash map. Now inside this hash map we are going to store 2 items. We are going to store the value as the key, and we are going to store the indices based on its value inside the hash map. So first we are going to check, okay, this one is value number 0, and currently the index values are 0, 1, 2, 3. So 0 is not present in the hash map. We will add entry 0 over here, and its index value 0 as well.
Grammarly now uses AI to help you write, not just revise. Type a prompt and generate a persuasive, mistake-free draft in seconds, personalized to your unique writing style. Download it for free at Grammarly.com.
شلونك كوفيلا؟ خۆشە کۆفێلا.
لەگەڵ خواردنەوەی قاوەی کۆفێلا ئەس بەو پەڕی شارەزای تێکەڵکردنی شیر و شەکر و قاوەکەی بکە. قاوەیەک پڕ لە تام و بۆن و هەستی ئیتاڵی.
Again 5 is also not present.